All right, let's dive into the fascinating world of large language models. We've all marveled at their incredible abilities. I mean, generating creative text, answering complex questions, holding these remarkably coherent conversations.
Absolutely.
But there's this fundamental challenge that crops up when we push these models to handle really long inputs, like an extended chat, a huge document, even trying to analyze a whole book.
Exactly. And the architecture that powers so many of today's really impressive LLMs, the transformer, it just runs into a significant memory bottleneck when dealing with those long sequences. It wasn't really built for, let's say, efficient long-term recall over vast amounts of information.
Right, and this challenge is tied to something called the KV cache, isn't it? Could you maybe break down what that is and why it becomes such a problem?
Sure. So think of the KV cache as the model's working memory for whatever input it's looking at right now. As the transformer processes each new bit of info, each token, it generates a key and a value representation.
Okay, these pairs get stored in this KV cache. Then, when it's looking at a later token, the model spits out a query and uses its attention mechanism to look back at all the stored keys in that cache, all of them, to find the most relevant values. That's how the model remembers earlier parts of the input and uses them to figure out what to say next. It's really the magic behind stuff like in-context learning. Okay, so it's kind of like building an index of everything you've seen so far, and then you query that whole index every single time you process a new word.
Precisely. And here's the critical part, the real bottleneck. That KV cache stores every single key and value pair for the entire sequence,
Wow.
which means its memory cost grows linearly with the length of the input sequence and also with the model's internal dimension size, D. So we call this O, scaling.
Right.
The longer the sequence and the bigger the cache gets. There's no upper limit. So for context with thousands or even millions of tokens, this just becomes computationally, well, way too expensive.
Ah, the dreaded ON. So that's the technical hurdle that puts a hard cap on how much context even the biggest transformer can realistically handle.
It really is. And because of this, a lot of research has gone into developing alternative architectures, ones that aim for much better efficiency, often trying to get memory costs that are constant regardless of how long the sequence is.
Like what kind of models?
Think models based on linear attention, or state space models like Mamba.
Constant memory sounds amazing, like no more endlessly growing cache. But the sources you shared, they point out that while these alternatives are efficient, they often, well, they fall short on key capabilities that transformers are great at, especially that high-fidelity recall, the associative recall, needed for good in-context learning. Why is that?
Yeah, that's the fundamental trade-off, really. Models like linear attention, they get their efficiency by approximating the full attention mechanism. So instead of keeping separate individual key value pairs in a big lookup table like the transformer does, they process past information sort of sequentially and collapse it down into a single fixed size hidden state representation. This hidden state acts like a recurrent memory, kind of summarizing everything seen so far.
So instead of keeping all the individual notes, it's constantly updating one single fixed summary.
Exactly. And here's where it gets really interesting, and this highlights the academic challenge these researchers are tackling. The source points out that this compression, this squashing into a fixed size state, leads to what they call memory collisions.
Memory collisions.
Yeah, when different pieces of information from the past, their keys and values get condensed and mixed together into this limited dimensional hidden state, they can actually interfere with each other.
Okay.
Imagine trying to represent, I don't know, many distinct patterns, let's say keys, by just mixing them all together into one single fixed blend that's the hidden state. If the original patterns aren't perfectly distinct, or orthogonal, as they say,
Right.
they kind of blur into one another in that blend. And that makes it difficult to accurately pull out just one specific original pattern later on when you really need it. This mixing and interference, it impairs precise associative recall, the ability to reliably get the specific value for a specific key from way back in the past.
I see. So the compression causes interference.
Precisely. And previous attempts to fix this in linear attention often use things like low-rank approximations, but those didn't fundamentally solve this collision issue that comes from the compression itself.
Got it. So efficiency gained by compressing memories, but you lose precision because things get jumbled up in that compressed state. And that brings us right to the core innovation of this deep dive. LoLA. The sources frame LoL as giving linear attention a smarter memory. What's the basic idea behind this smartness?
Right. So the core academic contribution of LoO, its smartness, it's based on this insight that not all memories are equally likely to cause these collisions in the compressed linear state. Some pieces of information are naturally easier to integrate into that global summary, while others are difficult, they get lost or they interfere with others.
Okay.
So instead of treating all memories the same way and just forcing them into that potentially lossy linear hidden state, LoLA uses a hybrid memory system. And it intelligently decides where each piece of information should be stored to get the best recall.
Okay, a hybrid system. So it's not just one type of memory component. What are the different parts then?
LoLA actually combines three distinct memory components, and it tries to leverage the strengths of each one. So first, you still have the efficient, constant memory linear attention hidden state. That's still the main component, great for capturing the global context and storing information that integrates well, the easy to remember stuff that doesn't cause collisions.
That's the part where the collisions can happen, though.
Right. So to counteract that, LoLA adds two components that use full rank attention, just like a standard transformer, but they're kept small to maintain efficiency. First, there's a sliding window attention. This acts like a high-fidelity short-term memory, perfectly remembering the most recent Ida Tarkin's Ida is just the size of the window.
Like keeping the last few sentences of a conversation crystal clear in your head.
Exactly like that. And this is really the paper's central academic innovation. The third component is a sparse cache. Now, this is a global full-rank memory, but it's designed to store only a limited number of specific key value pairs, let's say lambda pairs. And these can come from anyone in the past sequence. This is like a curated long-term memory specifically for that difficult information.
A curated long-term memory just for the difficult items. Okay, that's the smart part. But how does LoLA actually know which memories are difficult and need to be put into this special sparse cache?
Yeah, that's the clever bit. This is where their innovative scoring mechanism comes in, which they detail conceptually in equation 9. For potential key value pairs coming from the input, LoLA calculates what they call a self-recall score.
Self-recall score.
This score basically measures how well the current linear hidden state, that compressed summary, can reconstruct or predict the original value that was associated with a specific key.
Okay. So it takes a key, it uses the current global summary, the hidden state, to see what value it thinks should go with that key based only on the summary. And then it compares that prediction to the actual value that key was originally paired with way back when.
Precisely. A high score means there's a big difference. The current hidden state fails to accurately represent or recall that specific key value pair. This is LoLA's signal that this particular memory is difficult to remember within the current linear state. It's likely suffering from a memory collision, or it just doesn't align well with the aggregated summary.
That is a really clever way to diagnose the problem spots in that compressed linear memory.
It is, and LoLA uses the score to intelligently manage its memory systems. Key value pairs with high self-recall scores, those are the difficult ones, the ones prone to collisions, they get selected and stored separately in the high-fidelity sparse cache.
Okay.
Easy to remember pairs, the ones with low scores that the linear state can represent pretty well, those are the ones that get primarily integrated into the recurrent hidden state update. That's conceptualized in equation 12.
So it's like it's constantly checking each piece of information. Are you represented well by my general summary, my hidden state? And if the answer is no, it says, okay, you're special. You go into this high precision storage, the sparse cache.
That's the core of the academic contribution around the memory management, yes. And then when the model needs to generate an output token, equation 13 conceptually covers this, it retrieves information not just from that potentially lossy linear hidden state,
Right.
but also from the high fidelity sparse cache for those specific difficult details and from the sliding window for the very recent context. It combines information recalled from all three systems to make a more informed, accurate prediction.
And this whole process deciding what's difficult, updating the cache, updating this state that happens dynamically as new tokens come in.
Yes, absolutely. It's a dynamic process. As new tokens enter the sequence and old ones leave the sliding window, the main hidden state gets updated, as shown in equation 12. Potential candidates for the sparse cache, these could be pairs leaving the sliding window or pairs already in the cache, they get rescored.
Why rescored?
Because the difficulty of remembering them actually depends on the current state of the linear memory, which itself changes over time as it sees more data. So the cache is then updated based on these new scores and any potential new difficult candidates that have emerged. Equations 10 and 11 kind of conceptualize this cache update logic.
Okay, that's a really clear breakdown of the technical innovation here. The hybrid memory components, and especially that self-recall scoring mechanism to intelligently shuttle things between the efficient linear state and the high-fidelity sparse cache. So how does this clever system actually perform when they put it to the test? based on the sources?
Well, the sources present some pretty compelling evidence, particularly on tasks that are designed specifically to probe that long-range associative recall ability. A key benchmark they use is the single needle in a haystack task, or SNIH, from the ruler suite.
Needle in a haystack. Sounds descriptive.
It is. It involves embedding one single specific piece of information, the needle, somewhere deep within a very long document, the haystack, and then testing if the model can find and retrieve that needle. It's a direct test of overcoming those memory collision issues over really long distances.
Makes sense. And what did Table 1 show when they compared LoLA to a standard linear attention model? I think they called the baseline LoCats. What happened on these tough SNIH tasks?
Yeah, LoCats. Table 1 shows a really dramatic difference, especially as the context length gets longer. On SNIH1, where the haystack is just random sentences, the standard linear attention, LoCats, its performance just collapses. Accuracy drops from maybe 9% at 512 tokens down to less than 1% at 4,000 tokens.
Wow. Basically useless at that point.
Pretty much. And even adding just a sliding window doesn't stop this sharp decline. LoLA, however, with its sparse cache, maintains significantly higher recall. For example, their LoLA 1B model gets 99% recall at 512 tokens and still holds on to almost 70% recall at 4,000 tokens.
Huge difference.
And models with even larger sparse caches, like one they call LoLA 8B++++A, show almost perfect recall, even out to 4,000 tokens.
Okay, that jump in accuracy, especially on long context for finding those specific facts, that seems like a really direct validation of the whole sparse cache idea. The sources also mentioned that the type of haystack, like what it's made of, matters too, right?
Yes, they did observe that. Standard linear attention models, the LoLA, they actually did slightly better when the haystack was made of essay text compared to just random sentences.
Why would that be?
Well, the thinking is that essay structures are probably more similar to what the model saw during training, so maybe there are fewer inherently difficult memories or fewer collisions generated initially. But importantly, LoLA's sparse cache still provided a significant advantage on the essay haystacks at longer contexts, according to Table 1. So it shows the approach is robust even when the base linear memory is having a slightly easier time.
Got it. So it really tackles that long-range specific recall problem that just plagues standard linear attention. But what about general performance? Does it take a hit elsewhere? And is it still efficient?
Good questions. The paper addresses that. Table 3 shows LoLA performs competitively on a range of other more general benchmarks. This confirms it doesn't seem to sacrifice its general language modeling ability for this recall improvement.
That's crucial.
And importantly, for efficiency, Table 5 highlights something interesting. The sparse caching seems particularly beneficial for smaller models like the 1 billion parameter versions.
Why smaller models?
It's intuitive when you think about it. Smaller models have smaller hidden states, right? Which means they're more constrained capacity-wise, so they're probably more susceptible to those memory collisions we talked about. That makes the sparse cache's ability to offload the difficult memories even more impactful for them.
That makes sense. More collisions in a smaller space, so having that escape hatch is more valuable. They also showed good results with knowledge distillation.
Absolutely. Table 6 demonstrates that LoLA can be efficiently distilled from larger transformer models. When they compared it to other efficient model types distilled from the same teacher models, LoLA actually matched or even slightly surpassed the teacher model's average performance across various tasks. So it shows it can inherit the knowledge effectively while gaining the memory efficiency and the recall benefits.
Nice. And you mentioned visualizations. Sometimes seeing it helps grasp the concept.
Definitely. Figure 3 and Figure 6 in the paper are quite helpful. They visually show how errors in representing specific key value pairs just accumulate over time in pure linear attention. Figure 6, which focuses on relative error, clearly shows these initial small representation errors for early tokens just grow significantly as the sequence gets longer. That really indicates the corruption of memories in the hidden state because of collusions.
And LoLA.
By contrast, LoLA shows significantly reduced errors, particularly for those pairs that are strategically moved to the sparse cache. Those actually appear as zero error columns in the visualization, showing they're perfectly preserved outside the troubled linear memory. It's pretty powerful visual evidence that the sparse cache works in mitigating that collision-induced forgetting.
Yeah, seeing zero error for cached items really drives the point home. And there was an ablation study, Table 4, which seems key to proving that their specific way of scoring, their self-recall check, is the right way to pick which memories are difficult.
Exactly. That ablation study is crucial. It confirms that their self-recall check score, the one identifying pairs whose value is poorly predicted by the current hidden state, using their key is significantly more effective at picking which pairs to cache compared to other potential methods.
Like what other methods?
Like simply making the sliding window bigger or using other kinds of error signals, those alternatives didn't yield the same strong results. So it really validates their central hypothesis about diagnosing memory collisions within the linear state itself to intelligently guide the selective caching process.
Okay, this feels like a really significant step forward then in designing efficient LLMs that can actually reliably handle truly long contexts. Where does LoLA fit into the bigger picture, the broader research landscape?
Yeah, the sources definitely place LoLA within this growing wave of research into efficient long-range sequence models. They note the close architectural relationship between linear attention and things like state space models. LoLA essentially builds on that foundation by directly tackling the key weakness of these simpler linear models that struggle with high-fidelity associative recall because of the memory collisions.
And that concluding thought in the paper about how to design these efficient models, it felt important, focusing on where linear attention is already strong and then just complementing it where it's weak, rather than trying to force it to perfectly mimic softmax attention everywhere.
Yes, I think that's a really crucial takeaway. It suggests a more, let's say, nuanced approach is proving effective. You leverage the linear state for its great efficiency in handling the bulk of the information, the stuff that can be aggregated without too much loss. And then you use these higher fidelity but carefully capacity limited mechanisms like the sparse cache and the sliding window specifically for those critical details that would otherwise get lost or corrupted. It's really about intelligent resource allocation for memory.
So just to recap this deep dive into LoLA, the core academic innovation is really its hybrid memory system. It cleverly combines efficient linear attention with that short-term sliding window and the curated long-term sparse cache. And the real intelligence comes from that self-recall check score, which acts like a diagnostic, identifying which specific memories are hitting collision problems in the linear state and need to be offloaded to the high-fidelity sparse cache for safekeeping.
Exactly. And the sources provide pretty compelling evidence, especially from those needle-in-a-haystack tasks, that this innovative memory management significantly boosts associative recall over long contexts. It brings these linear attention models much closer to transformer performance in this critical area, all while keeping that impressive memory efficiency. It's a very targeted solution to a fundamental architectural bottleneck.
Yeah, it makes a lot of intuitive sense, doesn't it? Using the right kind of storage mechanism for the right type of memory, efficient, kind of blended storage for the general gist, but dedicated high-precision storage for those crucial little details that would otherwise just get washed away.
Precisely. It feels like smart engineering really grounded in a deep understanding of the architectural limitations they were trying to overcome.
So this definitely raises an interesting question for the future, thinking bigger picture. If the most effective approach we're seeing now for building efficient LLMs that have reliable long-range memory involves combining multiple types of memory, linear states, caches, windows, and selectively applying more resource-intensive methods, like full attention only where absolutely necessary, does this mean the frontier of efficient LLMs is going to look like these increasingly complex, sort of multi-component hybrid systems?
That's a great question.
Or is there maybe still a possibility of discovering fundamentally new, more uniform, but still highly efficient mechanisms out there that could achieve perfect or near perfect recall without needing this kind of hybrid complexity? What do you think?